Welcome to the class. Dear students, today we are going to discuss structural elucidation of benzene. It was in the year 1828 that a scientist named as Michael Faraday, he was experimenting on various gases of various compounds, and he found out, while experimenting on benzene, he found out that the vapor density of benzene is 39. So pointing that the vapor density of benzene is 39, he established the molecular formula of benzene to be C6H6. So scientists all across the world, now they were in the race to find out a structure that would accommodate this molecular formula. They were all in the race to find out the structure of benzene because now the molecular formula is known. So they were all in the race as to who will find it out first. But it was only in the year 1865 that a German chemist named August Kekule came closest to the structure of benzene. So what did he say? He said that benzene is a cyclohexagonal ring. It is a cyclohexagonal ring. It has 3 double bonds and 3 single bonds that are arranged in alternating fashion. And he also said that only one hydrogen atom is attached to each of the carbon atoms of the benzene ring. So let us see, what did he say? He said that benzene is a hexagonal ring of 6 carbon atoms. It has 3 double bonds and 3 single bonds arranged in alternating fashion, and each of the carbon atoms of the benzene ring has only one hydrogen atom attached to it. So he summed up his all findings into this single structure. But how did he do it? How did he do it? This is what we are going to see in this topic. So for this, the first thing that he tried to prove was that benzene is a ring. That was the first thing that he tried to prove. Okay, that is what we are going to study in section 1. Elucidation of ring structure of benzene. Elucidation of ring structure of benzene. So in section 1 we will study that. So first thing that he tried to prove that benzene is a cyclohexagonal ring. That was the first thing that he tried to prove. Okay, it is a cyclohexagonal ring. The second thing in this section only, what he tried to prove is that one hydrogen at one carbon atom. Okay, so these two things he tried to prove first, and these two things we will study in section number 1, which is elucidation of ring structure. First he tried to prove that it is a cyclohexagonal ring. The second thing is one hydrogen is present at each of the carbon atoms, is attached to each of the carbon atoms of the benzene ring. So this we will study in section 1, which is elucidation of the ring structure. In section number 2, the next thing that Kekule tried to prove was how many double bonds are there? How many double bonds? Double bonds, how many? Okay, and the second, under this section only, how are they arranged? How are they arranged? So this we will see in section number 2, which is elucidation of the bond structure. Elucidation of bond structure. So structure. Okay, so in the second section, what first Kekule tried to prove that it is a cyclohexagonal ring and one hydrogen is attached to each of the carbon atoms of the benzene ring. That we will study in section 1, which is elucidation of the ring structure. Then what did he try to prove? That how many double bonds are there in benzene and how these double bonds are arranged. That we will study in section number 2. Now the section 1, the findings of the section 1. Okay, I am telling you the findings beforehand only. The findings of the section 1 were that it is a cyclohexagonal ring. Okay, and one hydrogen, it is a cyclohexagonal ring. That is the findings of section 1. And second finding was one hydrogen is at one carbon atom, is attached at one carbon atom. Okay. From section 2, the findings were that there are three double bonds in benzene ring. And one more finding was there, that these three double bonds were arranged alternatively to each other. So based on these findings, based on these four findings, he drew a structure of benzene which was like this. So this was the structure that he drew. It is a cyclohexagonal ring, correct? One hydrogen atom is attached to each of the carbon atoms. Fine. There are three double bonds and they are arranged alternatively to each other. 1, 2, 3, and they are alternate to each other. So this structure was proposed based on the findings of the 2 section by Kekule. Okay. So for a time this structure was accepted, but later lot of objections came against this structure. Why? Because this structure was not able to explain a lot of chemical reactions that was actually shown by benzene. Benzene showed a lot of reactions. This structure was not able to explain those reactions. So as a defense to these objections, as an answer to these objections, what Kekule said is that this double bond, it is not fixed in the benzene ring. It will oscillate back and forth. That is, it will oscillate here and it will oscillate back. This one will oscillate here, it will oscillate back. This one will oscillate here and it will oscillate back. So that would mean that there is another structure of benzene. That another structure of benzene I am going to draw here. One hydrogen at each of the carbon atom, as previously. When this oscillates in this position, it would be here, this would be here, and this would be here. So there is structure 1, this is structure 1, and this is structure 2. So Kekule said that actually not one structure exists, but two structures exist for benzene, and these two structures, if it gave a viable defense against the objections that were raised during that time. Okay, so he said that what he meant to say is that if you take the benzene solution, the benzene solution will have both the structures of benzene, structure 1 as well as structure 2. It will have both the structure of benzene where these two structures will coexist with each other. So this is the final Kekule structure that was proposed. The final Kekule structure that was proposed. Our video, this is the part 1 of the video. Our video will stop after this. That is, till here only we will discuss in this video. That is till the completion of the Kekule structure. In part 2 of this video, we will see how the Kekule structure was proven wrong. Pardon. We will see how the Kekule structure was proven wrong. With the advent of new technology like X-ray diffraction methods, actually what is the issue is that when Kekule was doing the research, there were no newer technologies like X-ray diffraction method to see the structure of benzene. So whatever he found out through chemical reactions. And this was only his hypothesis, that it oscillates back and forth. This was just to explain many of the chemical reactions that benzene show, but were not explained by a single structure. So he gave an alternative structure and he said that this may oscillate back and forth. So it may happen like this. That is what he said. So it may, but there was no proof. So it was just a hypothesis. And this actually explained many of the reactions of benzene. So till that time, when X-ray diffraction method came, this was believed to be the correct structure of the benzene. Everyone believed that if you take a solution of benzene, there would be two structures, structure 1 and structure 2, and they would coexist with each other at room temperature. So both these structures were believed for a big amount of time, till the advent of X-ray diffraction method. When X-ray diffraction method came, the Kekule structure was proven false. The Kekule structure was proven false. So with the help of X-ray diffraction method, what we came to know is that these double bonds, no? How many double bonds here? 3 double bonds. These 3 double bonds means 6 pi electrons, right? 6 pi electrons means 6 p orbitals, right? 6 unhybridized p orbitals of carbon, because each carbon is sp2 hybridized. 6 p orbitals. These things, whatever you can say, whatever you call them, these things are actually shared by the 6 carbon atoms equally. That is, 6 pi electrons are shared by 6 carbon atoms equally, and each carbon atom has an equal share on the 6 pi electron. That is what X-ray diffraction method showed us. Okay, here look at this. This pair of electron, look at here. This pair of electron is actually shared by only 3 carbon atoms. 1, 2, 3. Correct? This all is shared by 3 carbon atom. 1, 2, 3. So this is what Kekule said. But it is not this case. What X-ray diffraction method shows us is that this pair of electron is shared by the 6 carbon atoms equally. This pair of electron is also shared, and this too. So that is a difference. So that results in a structure like this, where all are having equal share of electrons. Okay, all are having equal share of electron. So this structure is referred to as the resonance hybrid structure of the benzene. It is referred to as the resonance hybrid structure of benzene, and this is the correct structure of benzene. So can we say, or should we say, that the Kekule formula is a false one? Is it totally false? It is false, of course, but is it totally false? No, it is not totally false. He is almost correct, but not fully correct. He is the closest to the structure of benzene. He proposed structures which were closest to the structures of benzene at that time. It's not totally false. So while writing chemical reactions, we use this resonance hybrid structure of benzene, which is like this. When we write chemical reactions, we just show benzene like this. We use the resonance hybrid structure. But to understand the mechanism of reactions, we still use the Kekule structure of benzene, which is this. Either we use this or we use this, right? Because this is almost correct. That is why we use Kekule structure in understanding the mechanisms of reaction that involves aromatic compounds. Okay, so that when we use Kekule structure, it helps us to better understand the mechanism of reaction. But when we are writing reactions, we are using the resonance hybrid structure of the benzene. Okay, I hope it is clear. So that the Kekule structure is a false one. It's not fully correct. It will be discussed in part 2 of this video. Right now, let us turn our attention to part 1 of the video. Welcome to the first part of this video. In this video, we are going to see structural elucidation of the Kekule structure of benzene. We are going to end where Kekule ended. We are not going to see the resonance hybrid structure of benzene. One thing you people have to understand is that during the times of Kekule, the technology was not so advanced. So whatever findings he had done through chemical reactions only. The findings that came out of chemical reactions only. So he didn't see anything through X-ray diffraction measurement. So because of these limitations, the proposed structure that he gave, it was not fully correct. He was almost correct, but not fully, right? So we are going to stop where actually Kekule stopped, that is at the false structure of benzene. Okay, and as I said earlier in the introduction part, he was almost correct. So still, therefore, the Kekule structure of benzene is still used in understanding mechanisms of those reactions that involve the benzene ring. Okay. Now, how did Kekule prove the structure of benzene? For this, he first tried to prove that that it is a ring, cyclohexagonal ring, right? It is a ring structure. That is what he tried to prove first. Then he tried to prove that one hydrogen atom is attached to each of the carbon atoms of the benzene ring. So this we will study in the first section, right? In the second section, we are going to see how it is, how many double bonds are there and where it is located. What is the location of these double bonds? That we will see in the second section, right? And out of these, the findings will come out. So let us now start with the first section, the establishment of ring structure of benzene. So as I said, the molecular formula of benzene was established to be C6H6. So Kekule, what he did, he was also a normal scientist. So what he first thought was that benzene is a aliphatic unsaturated hydrocarbon. It is a alicyclic unsaturated straight chain hydrocarbon. Okay, straight chain aliphatic unsaturated hydrocarbon. So he draw the possible structures of unsaturated straight chain hydrocarbons that would accommodate the molecular formula of C6H6, right? So he draw those possible structures that would accommodate this molecular formula. So he drew this structure, he drew this structure, he drew this structure. All of this molecular formula is C6H6. So these are the possible structures that he found out first, right? Then he did chemical reactions for benzene. Okay, he did chemical reactions for benzene, and benzene, he found out that benzene do not show any of the characteristic reactions of alkenes or alkynes, right? So it is not, he found out that it is not a straight chain hydrocarbon, because alkenes and alkynes are actually straight chain hydrocarbons, right? Aliphatic straight chain hydrocarbons, and benzene do not show any characteristic reactions of such hydrocarbons, right? So these structures were outrightly, it was rejected. These structures were rejected because benzene doesn't show any reactions, any characteristic reactions of alkenes and alkynes. So these structures were rejected by Kekule himself. Then how did he come? The other way of thinking is, if it is not a straight chain structure, then it would probably be a ring structure. It would probably be a ring structure. So how did he prove the ring structure of benzene? That is a question. For this, first he conducted hydrogenation. He conducted hydrogenation of benzene. Hydrogenation of benzene. So what he did in this, let us see. He took the benzene and just simply hydrogenated it. Hydrogenation is addition of hydrogen. Okay. So what he got was a cyclohexane molecule. It was a cyclohexane molecule. Now the structure of cyclohexane was already known at that time. It was already known that cyclohexane consists of 6 carbon atoms in the form of a cyclohexagonal ring. Okay, it was known at that time. Okay, leave it like that. We will come to it later. Now hydrogenation is a reaction where hydrogen gets added, and it is just involves addition of hydrogen. There will be no change in the structural framework of carbon atoms. There will be no change in the structural framework of carbon chain. That is, the carbon chain, it will have no change. It will have no change. It will remain the same. Just it is that the hydrogen gets added. So if the cyclohexane is composed of 6 carbon atoms, which is in the form of a cyclohexagonal ring, then it is very sure, it is inferred that benzene is also a cyclohexagonal ring composed of 6 carbon atoms. Composed of 6 carbon atoms. So this is the first observation that Kekule made. I hope it is clear to you. What is it? How did he come up with the ring structure? What is the first proof? He carried out the hydrogenation of benzene. He got cyclohexane. cyclohexane was already known at that time to be a cyclohexagonal ring of 6 carbon atoms. Leave that aside. Come, what is hydrogenation? Hydrogenation is just the addition of hydrogen. There is no change in the structural framework of the carbon chain. So that means hydrogen has got added and there is no change. That means the structure that cyclohexane has, what is it? A cyclohexagonal ring of 6 carbon atom. That would be the same of benzene, right? It would be the same with benzene. That is, benzene is made up of 6 carbon atoms held to each other in the form of a hexagonal ring. Fine. This is the first one. Now what is the second proof? The second this thing is bromination of benzene. Bromination of benzene. Bromination of benzene. So benzene was brominated. Benzene was brominated. So for bromination, what you need to do is, you have to heat it with FeBr3 and you have to boil benzene. You have to put FeBr3 and you have to boil benzene. Fine. So bromination takes place in this way and this is the result. Right? This is the result. Okay. Now it is attached here. What is the product you get? 1-bromobenzene. Okay. Now suppose it is attached here. What is the product you get? 1-bromobenzene. Okay. Now suppose it is attaching here. What is it? 1-bromobenzene. Here also 1 bromo. Here also 1. Here also 1. So you are getting, when you are brominating benzene, you get only 1 bromobenzene. 1 monosubstituted bromobenzene. Only 1. And there are no 2 bromobenzenes. There is only 1 bromobenzene. So that indicates that benzene is in the form of a cyclohexagonal ring. Right? If it was not a ring, you would have get many positional isomers for bromobenzene. Right? But because it is in a ring format, wherever the bromine gets attached, doesn't matter, you will get only 1 bromo substituted benzene. Right? So this is the second proof that benzene is a cyclohexagonal ring. Okay. Now the third proof is, when you continue with the bromination, that is, if you are still heating with FeBr3, then you get 3 kinds of, okay, I'll just go for the third proof with bromobenzene. I'll start with bromobenzene. So if you are continuing to heat it, you are continuing to brominate it, okay, you get 3 dibromobenzene, 3 kinds of dibromobenzene. This is the first one, this is the second one, one 3, and this is the third one. Right? This is the 1 2 dibromobenzene, 1 3 dibromobenzene, 1 4 dibromobenzene. You will get only 3 dibromobenzenes if you brominate bromobenzene. So that indicates that it is in the form of a ring. Why it indicates? See, why only 3 dibromobenzene? This is because here position number 2, 3, 5, 6. Position number 2 and 6 are same, right? If bromine is here, doesn't matter. You will get 1 2 dibromobenzene only, right? Position number 3 and 5 are also same. Whether bromine is here, it doesn't matter. You will get 1 3 dibromobenzene. And position, here it is only one position. So wherever it is coming, it will go for dibromobenzene. So you will get only 3 kinds of dibromobenzene, and this 3 kinds of dibromobenzene is only possible if the benzene is existing as a cyclohexagonal ring. Otherwise it is not possible, right? So this is the third proof that benzene is a cyclohexagonal ring. It is a cyclohexagonal ring. Similarly, if you are continuing with bromination again, if you are again continuing with bromination, you will get tribromo substituted benzene. That too, it will be 3 types of tribromo substituted benzene. So that is only possible if benzene is in the form of a cyclohexagonal ring. So that is the 4th proof of benzene being a cyclohexagonal ring. What I mean to say is that if you are again going for bromination, okay, you will get tribromobenzene. Okay, you will get 1, 2, 3, right? Tribromobenzene. Then you will get 1, 3, 4, right? So you will get 3 types of tribromobenzene like this only, and that is possible only because benzene exists in the form of a cyclohexagonal ring. So these are all the proofs that benzene is a cyclohexagonal ring, right? And what is the proof that only one carbon atom one hydrogen atom is attached to one carbon atom? The proof is here. See, I will show you the proof. If you are brominating benzene, the first bromination, only one bromine atom gets attached to one of the carbon atom, right? So that is a proof that only one hydrogen atom was initially attached, okay, and after removal of that hydrogen atom, only that bromine atom has come as an electrophile, right? So this reaction is the proof that only one hydrogen atom is attached to each of the carbon atoms in the benzene ring. Okay, so in section 1 we have proved 2 things. One, that benzene is a cyclohexagonal ring composed of 6 carbon atoms, of course, is a ring that has 6 carbon atoms existing as a cyclohexagonal ring. It exists as a cyclohexagonal ring. The second thing that we have proved in this section is that only one hydrogen atom is attached to each of the carbon atoms in benzene, right? And the proof of it is that bromination of benzene yields monobromobenzene, okay, not dibromobenzene. It yields monobromobenzene. That is, one bromine atom attaches to one of the carbon atoms of the benzene. That means that each of the carbon atom is having one hydrogen atom attached to it. Okay. Now, in section 2, we are going to see, now we start section 2. In this section, we will see how Kekule proved that there are 3 double bonds in benzene, and how he proved that these 3 double bonds are arranged in an alternative fashion to each other. So section 2 is referred to as elucidation of the bond structure of benzene. Elucidation of bond structure. So how he proved? Any guesses? Students, come on. How he proved that there are 3 double bonds in benzene? How did he prove? Any idea? We have already shown the reaction. Yes. If anyone remembers, this is the reaction. Benzene, it adds 3 molecules of hydrogen and it gives cyclohexane. So for every molecule of your benzene, 3 molecules of hydrogens are needed. For 1 mole of benzene, 3 moles of hydrogen is needed. So that means for 1 molecule of benzene, 3 molecules of hydrogen are needed. 3 molecules of hydrogens are needed means 1 hydrogen molecule, that is 1 H2, actually binds to 1 double bond. So 3 H2 will bind to 3 double bonds. So that means that there are 3 double bonds in benzene. That means that there are 3 double bonds in benzene. I hope you understood this. We have already seen this reaction where benzene is giving cyclohexane on hydrogenation. This has proven that benzene is a cyclohexagonal ring. Initially in section 1 we have proved it. It also proves one more thing. That one thing is that 3 moles are needed for 1 mole of benzene. 3 moles means 3 molecules of H2 are needed for 1 molecule of this thing, benzene. Now one hydrogen actually combines to one double bond. Three hydrogens would combine to three double bonds. So as three are needed, it means that there are three double bonds in the benzene ring. Three double bonds in benzene ring. So that is why how we found out that there are three double bonds in the benzene ring. Now the second thing that was coming as a question in August Kekule's mind was, where are these three double bonds located? So we will see that now. He conducted ozonolysis. So what did he do in ozonolysis? Let us see. So this is the benzene structure, and you conduct ozonolysis. Take three molecules of ozone. O3 is ozone. You take three molecules of ozone. So you will put a dot like this and split it like this. Okay, otherwise you may not be able to draw. Now you draw a triozonide. For drawing a triozonide, it's very simple. You draw CH like this, then you go for O, then you draw a CH here, draw another CH here, connect it with CH, connect this with CH, connect this with oxygen, fill oxygens, we are filling three oxygens, right? So this is a triozonide. Now this triozonide, it will split automatically, it will split and it will give you something like this, glyoxal. It is called as glyoxal. The formation of glyoxal indicates that there are three double bonds in benzene. Just see how many molecules of ozone are added. 3 molecules of ozone are added. How many double bonds are there? 3 double bonds. One ozone molecule binds to one double bond. You can see wherever there was double bond, here there was double bond, here there was double bond. Wherever there was double bond, ozone is getting added. One molecule of ozone is getting added, right? Here there was no double bond. Look, so it is no double bond. See, here ozone is not getting added. Then you are seeing here double bond, right? So here ozone is getting added. Then there is no double bond here, so no ozone is getting added. Then there is a double bond here, so ozone is getting added. So ozone is getting added at places where there are double bonds. So it proves two things. It is adding alternatively, right? Not everywhere, right? It is adding in alternative fashion. So that proves that double bonds are arranged in alternative fashion. It also proves that there are 3 double bonds, right? So this single-handedly proves that there are 3 double bonds, because one ozone molecule binds to one double bond and 3 ozone molecules have been binded. And it also proves the positions of the double bonds, right? They have added in the alternative position. So that means there are 3 double bonds in benzene and they are arranged in alternative fashion. So that completes your section 2. Now what are the findings of section 1? What are the findings of section 1? The first finding was that it is a cyclohexagonal ring. There were a lot of proofs. 5 proofs we gave for cyclohexagonal ring. The first one was hydrogenation of benzene to cyclohexane. The second was bromination of benzene. We formed monobromobenzene. Third was again bromination of monobromobenzene. We formed 3 kinds of dibromobenzene, right? Then again bromination when we did, we formed 3 kinds of tribromobenzene. All these are proof of cyclohexagonal ring structure. We found that one hydrogen atom is attached to each of the carbon atom. The proof of that was that on bromination we got only bromobenzene, monobromobenzene. If there were 2 hydrogen, we would have got dibromobenzene. So when we carried bromination, we got monobromons. So that means that one hydrogen atom is attached to each of the carbon atom. So this is the findings of section 1. Second section's finding were that there are 3 double bonds and they are arranged in alternative fashion. So this was where Kekule summed up his work. So this, he said that benzene is a cyclohexagonal structure of 6 carbon atoms, each 6 carbon atoms which are held to each other by 3 single bonds and 3 double bonds arranged in alternative fashion, with each carbon atom attached to only one hydrogen atom. That is what Kekule said, and this is the sum up of his work. This structure is the sum up of his work. Now, for a little bit of time, this structure was okay with everyone, but soon objections were raised against this structure. Why objections were raised, I will tell you, and that we are studying in section 3, objections to Kekule formula. Section 3, objections to Kekule formula. Objections to Kekule formula or Kekule structure. That would be much apt for those who fear maths. Yes. Objections to Kekule structure. Now, if the structure of benzene is like this, okay, as proposed by Kekule, I am going to draw the same structure here. This is the structure as proposed by Kekule, right? He said that there are 6 carbon atoms arranged to each other in the form of hexagonal ring, 1 hydrogen atom at each of the carbon atoms, 3 double bonds in alternative fashion. If this is the structure of benzene, then if you are conducting bromination and if you are forming bromobenzene, then again if you are conducting bromination, you form what? Dibromobenzene. Fine. So there can be 2 kinds of ortho-dibromobenzene. This is the first kind of ortho-dibromobenzene, and this is the second kind of ortho-dibromobenzene. What is the difference between these 2 kinds? I hope you understood. You are following up. If this is the structure of benzene as proposed by Kekule gave only this structure, right? He only proposed this structure, right? He said that okay, these are in alternative position, right? So if this is the structure of benzene, if you are carrying out bromination of monobromobenzene, then what would form? 2 kinds of ortho substituted dibromobenzenes will be formed. One in which the bromine atoms are attached to carbon atoms containing double bonds. Carbon atoms containing double bonds. And one in which bromine atoms are attached to carbon atoms containing single bonds. Right? So 2 kinds of dibromo substituted benzenes are formed. 2 kinds of ortho dibromo substituted benzenes are formed. One in which the bromine is attached to carbon atom containing the double bond. The other in which bromine atom is attached to carbon atoms containing the single bond. If this is the structure of benzene. Okay, that is what the scientists said, right? They asked Kekule regarding this. But they also said that we know that only one kind of ortho-dibromo substituted benzene is formed. When we experiment, then what we found that there is only one kind of ortho or dibromo substituted benzene that is formed, right? There are no 2 kinds. Are there 2 kinds of dibromo substituted benzene at ortho positions? No, there is only one kind of ortho dibromo substituted benzene. There are no 2 kinds. So that means there is some problem with the Kekule structure. So as a viable defense, he said that the double bonds in the benzene molecule, they are not fixed. They oscillate back and forth. Let me write the double bonds clearly. They are not fixed. They oscillate back and forth. That means this double bond, it can come here, then it can go back. And this double bond, it can come here and it can go back. And this double bond also, it can come here and it can go back. So that means that there are two structures of benzene, right? The other structure, this double bond will be here, this will be here, and this will be here. So there are two structures of benzene that actually Kekule proposed now. He said this is the second structure of benzene. He said that if you are taking a solution of benzene, let me now rub the arrow. So he said that if you are taking a solution of benzene, a bottle of benzene, and if you are observing the solution of benzene, there will be two structures of benzene that coexist with each other in that bottle. Okay, there will be this kind of benzene in which the structure is like this, and there will be this kind of benzene, and they do interconvert among themselves. So this is the final Kekule formula which Kekule gave, and this actually explained this kind of reactions, right? If this is the case, if they oscillated back and forth, then there is of course only one ortho dibromobenzene. Then there will be only one ortho dibromobenzene, right? Because it will be very difficult to find out. So there will be only one ortho dibromobenzene. But if this is the structure, like if the double bonds are rigid, if they are fixed as initially proposed by Kekule, then there will be two orthodibromobenzenes. One in which the bromine atom will be attached to carbon atom containing double bond, and the other in which the bromine atom will be attached to carbon atom containing single bond. But we already know that this structure, that we only get one orthodibromo and not two orthodibromo. So Kekule, he came up with this new theory that it actually oscillates. So that is why we are getting one ortho. That may be the reason that we are getting one orthodibromo. He didn't have any proof at that time. The technology was not so advanced. He was almost correct for the structure of benzene, right? This kind of explanation, this kind of his explanation, that is oscillation of electron pair, this explained most of the reactions of benzene ring. Okay, so he was almost correct. He was the person who has come closest to the structure of benzene. So now we know. So here this video ends. In the part 2 of this video, we discuss that the Kekule structure is not the correct structure of benzene. He was almost correct but not fully correct. We now know that there is no oscillation happening. There is nothing as oscillation which happens. We know that the 6 pi electrons, that is 3 double bonds, they actually are shared among the 6 carbon atoms, right? And that sharing is equal. Okay, and that leads to another resonance hybrid structure. When, as said by Kekule, when oscillation happens, this pair of electron is actually shared by 3 carbon atom, right? When oscillation occurs. But that is not right. This electron pair is actually shared by the 6 carbon atoms, and that is what we will discuss in part 2 of this video class. So here is this is the structure where finally Kekule ended. Dear students, I hope you have understood this class. If you have understood it, please do not forget to like, share and subscribe the channel. Thank you very much.